Hey, what's up, guys? This is Chung here. So today, today's daily challenge problem number 1048, longest string chain, right? So you're given like a list of words, right? And and then and this it defines like a word one is a predecessor of word two, or even only if we can add exactly one letter into word one to make it equal to word two. Right? For example, ABC is a predecessor of ABAC because we add A between the B and C. Okay, and then our task is to find like the longest possible chain of sequence in a given word list. Basically, a chain is that each of the each of the word is the predecessor of the next one, right? And we just need to return the longest length. For example, right, we have this one here. The longest chain we have is 4 because we have A, BA, BDA, and BDCA, right? And that's it. So, and the constraint is like this. It's not very strict constraints. Only 1,000 words at most, and each word is only at most 16 length. So, actually, the moment I saw this problem, the first thing came to my mind was like this one is very similar to that very classic problem. It's called LIS, right? Which represents for the longest increasing subsequence, right? Where in this problem you are given like a bunch of numbers, integers, right? And you need to find the longest increasing subsequence among those. So this one is similar, basically, because the basic since the chain could end at any location, right? That's why we have to try all the possible scenarios, But in order to try that, first thing first, we have to sort it so that we can only we'll look back because if we don't sort it, if the current one, if the word one is longer than the word two, right? Then obviously there's no way uh this word one can be a predecessor because we need to add like one letter to the predecessor. So after sorting these words here, so what's left? Basically, we can use the DP, so the DPI here. So this one means what? The DPI means that ending with the ice word. What's the longest chain? The longest chain of predecessor we can get. So a little bit about this DP here, So the reason we can use DP for this problem is that let's say we have a DP, we have a I word. So we have a word I here, right? Word I here, and then before the word I, let's say we have word J1 and then word J2, right? So if we know, right, if we know the J2 is a predecessor of the current I word, it means that we can basically create a bridge, right, or a chain this word in this problem from the J2 to I, right? So if we know the DP of J2 here, right? So if we know this one, if we know by the end of this J2, if we can like make if the longest chain at the end by the end of this J2 here is let's say for example if this one is 2, then we know if we build after building the bridge from J2 to I, the longest one we can get the long no, not I mean the bridge, so the length of the chain we can get for this path is 3 because we're gonna add 1 here, right? So similar from J1 here, right? So if we have another one, if J1 is also predecessor of the I here, we can also build like a bridge here, right? So let's say this one, the DP of this one is 3. That's why we'll have like 3 here. We'll have 4 here, and we'll always get the longest one. So, and the reason we can use DP here is that because we can break this problem into a smaller problem. Basically, after we getting the longest one of the previous word here, we can use that to calculate the current one, because the current one, you know, the current one will not affect the previous one, right? As long as if this one is fixed, but if the longest one is fixed, then we can certainly use that to calculate the current one. And once we finish calculating the current one, we can also use this one to calculate the later one, right? And that's our logic, right? So at each of the I word here, we go back to check all the previous words, right? If any previous words is a predecessor of the current one, then we'll try to update the current one with a previous with that word's DP value, right? So in the end, we can get the longest one here. And this one is exactly the same logic as LIS, which is like using the same logic here. The only difference for this one is that in LIS we can simply compare the value of the two integers to determine if we can build a bridge, an edge, right? But for this one, we have to create like helper functions to determine if this one is a predecessor of the current one, right? So I guess we can just start implementing that, but the one we are implementing here, it's not the fastest one. We start from this one because this one is the most solution came to my mind, and after this one, we're gonna implement improve this solution into a better one. So first, let's define the helper functions. Let's call it its predecessor, right? Predecessor. So we have a word 1 and word 2, right? I mean, there are like many ways you can define this, implement this helpers. I'm just showing you guys the one I have here. And it's a little bit long here, so and first we check if the n1 plus 1 does not equal to n2, right? So if the diff is not 1, then we simply return false. Otherwise, I have a find diff equals to false, and then we have I dot j dot I equals to j equals to 0, right? We need 2 pointers to loop through to compare the letters one by one, right? So while I is smaller than n1 and j is smaller than n2, so we check if the word 1I is not equals to word 2j, right? Then we check if we have already find the difference before, then it means that false, right? Else what? Else we increase the j plus 1 and then we mark this find difference equals to true. So here, so if this is the first time we find a difference, right? We simply just we just add like one letter to the first word to match with with the j. That's why we only increase the j here. And else, right? So else we increase the pointers for both. Okay, and if everything works fine, we return true. That's it. All right, so that's the helper functions. And then, like I said, we're gonna sort this word first, right? By the length, right? So which means we're gonna need the like lambda function, x dot, and then x is gonna be a length of x, right? And then we need the n of length of words, okay? And then we need a dp, right, to store the value, right, at each index here. And we start from 1 because a word itself can at least form a chain with the length 1. Okay, and then we just loop through each word, right? And then for each word, we go back to check all the words. If the predecessor, right? Predecessor. If the predecessor of words j of words I, right? And then we update the current DP, right? DPI is going to be the max of DP I and the DP j plus 1, right? That's it. And then in the end, we simply return the max of DP. So here, this is because, because the chain can end at any index. That's why we have to check all the DPs. Remember, so the DP we're defining here is that, ending at the current one, right? The chain ends at this index. That's why we have to check all the DP here. Okay, let's run it. Okay, accept it. Let's run it. So cool. It passed, right? But as you guys can see, this one only beats 10%. And the reason being is the time complexity. Because so we have a nested for loop here, that's why time complexity for this one is like n squared, right? Let's say the length is n and the word's length is m. So which means this time complexity is n squared times m, because the predecessor we have 2 pointers, and right, we loop through the entire word. And yeah, that's why this one is a little bit slower. The reason being is we have n squared on this n here, right? So what can we improve that? Actually, there's a better solution, which is since this word is much smaller, the length of word is much smaller than the length of the words list. So instead of looping back each word here, what we can do is that we can try to delete each letter on the current word, and then we get a new word, right? And then we just need to check if the new word exists in the words we have seen seen so far. If it is, then we know, okay, we know we can build similarly we can build the edge from that word to the current one, right? Yeah, so which means then let's do that, right? So like I said, instead of looping through all the previous words, we can just try to remove each letter from the current word. So the current word is going to be the words of I here, right? And then and with the new word here, we're gonna have we will need to have the word as a key to store the length of the chain ending with that word. Because here we're using an index here, but here we're using a word, which means we can change this one from a list into a dictionary. Okay. So basically, for each of the word here, the current max number is going to be 1, right? Because we don't have a default value for this. So this one means similarly, because the word itself can be a chain, right? And then for j in range of length of word, okay, we try to remove the current j's letter. So the new word is going to be a word of j plus word of j plus 1, right? And then if the n word is in DP, right? Because since we're processing the words from left to right, right? So currently, at this line here, the words in DP are the words on the left of the current word, right? Which is the word which is smaller, has smaller length of the current one. So if this new word is in the DP, which means that this new word exists in the previous word, then we can just build like an edge, right? Bridge. So which means we can update the current max with that from that word, from that n word. So it's going to be current max of the DP of n word plus 1, right? And then here we just update that word with the max, right? So that's it. And here, since we're using like a dictionary, we just need to do a values, right? And that's it. So if I run this code here, accept it, and if I run it again, so boom, right? So now it's much faster, only 100 milliseconds. And the reason is also very obvious, because now the time complexity is we have an n here, right? And then here we have for loop, but this time the for loop is what? For loop is m. It's the length of the word. and in each of the the loop here, we concatenate the word, which is another m. That's why this one is n times m squared, which is much faster than the previous one, right? Cool. I think that's it, right? I mean, it's very classic, like DP, LIS problem, a little bit of variation. And yeah, thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.